Okay. Well, today we are going to look at the GPS a little bit more in depth, and we're going to study some of the sources of errors and try to translate physical layer communication link parameters into hardcore estimates of performance and location accuracy. You didn't do that last time, did you? No? No, I think you got just sort of an overview and talked about what the GPS constellation consisted of, how it basically worked, the fact that you get pseudo ranges, which uses spread spectrum to figure out when a signal arrived from Earth, from the satellite to Earth. You know a priori what the satellite orbits are, so if you know what the time is, and you get the pseudo range, you pretty much know the distance that it took from the satellite to that location. Now, of course, there's sort of this offset delay. You can't measure absolute time very precisely on Earth without synchronizing to GPS, so it's sort of a chicken and egg problem. But you can basically, you can calculate the distance plus some sort of offset factor that shows up on all the other satellites that you measure too, so it becomes just another unknown in your analysis. And so really, you need how many satellites to triangulate a 3D position with GPS? 4, right? You got X, Y, Z. Those are your unknowns, but there's also this offset time delay. And I believe Dr. Stepp has talked to you about how to derive the equations of triangulation and showed you how to, at least what the system of equations are. It's a nonlinear system, so it's not the easiest thing to solve, but you can actually take the linear combinations of them and subtract out the quadratic terms and do some solutions. That might be your next homework, actually. I usually give like a couple of pseudo ranges from some satellites, and you have to find where in Atlanta I'm talking about. So maybe we'd do that one in groups. That would be kind of fun. I don't know. I haven't made up my mind yet. So yeah, now we're going to talk a little bit more about the in-depth issues and how to get precision estimates out of our link parameters. So any questions? Yeah, Josh, right?
Yeah.
Okay.
What information is the satellite sending down?
Oh, that's a good question. So riding on top of the spread spectrum signal that you're actually using to do the ranging is a data sequence. And in fact, I even have a slide on that. I can pull this up. Ah, here it is. So let me go ahead. Let me see if I have a paper copy here. Here we go. This is a plot of the data structure of a waveform that's actually riding on top of the spread spectrum down to Earth from each GPS satellite. It's a very slow waveform. It's only 50 bits per second. But there's not really a lot of need for throughput on that waveform because it's really just supplementary information to help you with the decoding of your signal, to help a receiver decode the signal. So for example, there are these like 5 subframes, and it takes about 30 seconds to do these 5 subframes. Each subframe lasts about 6 seconds. That means it's got about 300 bits in it. And it's got like a little preamble so you can synchronize with it. This telemetry word, another piece of information used for synchronization. And then each subframe, the first subframe always has clock correction and satellite quality. So basically information that tells you how the onboard satellite clock is performing. So you sort of like tells you the exact time as synchronized from the first arriving bit in the message. And it'll also tell you the quality of the satellite. You know, is this a trustworthy, reliable satellite that's part of the system, or is this one of the GPS satellites that maybe they've just turned it on and maybe it's not reliable, maybe it's not in good health, it's steered out of orbit or something like that. There's a provision in there to identify unhealthy satellites. Then the next two words, these data chunks on the next two subframes are called ephemeris. And ephemeris is sort of a measure of how badly out of orbit is the GPS satellite. Remember those range equations that Dr. Steph has covered last class period? Assume that you know where the satellite is. And we know from our orbital mechanics that satellite orbits are very predictable. If you know what the time is, and you know what satellites you're dealing with and what their initial conditions were, you should be able to pinpoint it very precisely in its orbit. However, we also know that there are some oblations and some irregularities. And over time, unless you're just constantly exhausting station-keeping fuel, there'll be a little bit of a tug left or right and slow down, and enough to make a dent in your accuracy for GPS. Because remember, we're trying to pinpoint things within plus or minus several meters with GPS. We want to be able to, a few meters of error in a position of a satellite that's zinging around the Earth is going to make a big difference in that calculation. And so ephemeris will tell you sort of how far out of whack that is. And you can use that in your corrections when you go to recompute your position estimates. Yeah, Alec, did you have a question or comment?
Are modern receivers able to compensate for the ephemeris?
Are what?
Are modern receivers able to compensate?
Some of the nice ones can use this information to compensate for it, yeah. Yep. Let's see, the next line is data almanac and ionospheric and UTC correction. So this is ionospheric correction would be like, you know, trying to estimate what the propagation delay is through the ionosphere roughly in the area of the satellite. So the satellite is going to be directly over some spot on the Earth. And the ionosphere is kind of a strange phenomenon. It changes. It almost has like its own weather, you know. It's different in different parts of the Earth. And it's also different during different parts of the day when you have a lot of solar radiation coming down, sunlight hitting the ionosphere. It warms up and you get more ions. You get more charged particles as well. When it's turned around to the back side of the Earth, the charge density goes down, which means the propagation delay is going to change as well. So for that, there's a very crude correction factor that they'll add into the satellite that you should be able to decode and use that to increase the accuracy. And then this last block is called the almanac. And actually, there's a whole bunch of blocks that are considered the almanac. It's not very critical information. So chunks of the almanac are sent, you know, every fifth frame. And it probably takes several minutes for the actual, it actually says right here, a super frame consists of 25 frames of 30 seconds or 750 seconds, 12.5 minutes, and provides a complete almanac. So the almanac basically tells you the history of the satellite, any other interesting information that you may want to know about the satellite. But it's generally not critical for discerning your position. So anyway, that's the data that's riding on top of the signal. And some of it's actually pretty helpful. We'll talk about these in a little bit more detail when it comes to correcting some GPS errors. But first we have to figure out what those errors are. Okay. So let me make a chart on the board. GPS precision. Types of errors. So what are the sources of errors in this decoding scheme and position estimate scheme? I'm going to list each one, and basically I'm going to list how much their standard deviation error is in position estimate that they contribute individually. So in the absence of any other errors, how much error in terms of meters would this contribute to your GPS position estimate? And think about, they are going to be reported as a standard deviation. So we know that's kind of like plus or minus a standard deviation captures about 2/3 of the cases if you assume a quasi-Gaussian distribution. So if we have a 3-meter error, that means that between the estimate and the ground truth, 2/3 of the time they will be less than 3 meters apart in any particular direction. So let's list all the errors. One is satellite clock errors. And in the absence of any other error, its contribution would be about 3.5 meters. So this is just a synchronization issue with the satellite, with your receiver and the satellite clock, and the master clock basically in that mountain out in Colorado where they do the atomic clocks and synchronize the entire GPS system. You know, ultimately, this positioning system is based on the fact that you can measure time very accurately. In fact, if you think about it, that's like the only thing we actually can measure very accurately in electrical engineering. Time is the one thing that we can measure to arbitrary degrees of precision, practically. Everything else is sort of based on time. So satellite clock errors, 3.5. This ephemeris error that we were talking about, the fact that the satellites are going to be just a little bit off, that'll contribute about 4.3 meters. In fact, I'm going to assign a variable to each of these because I'll put up an equation in a second that uses them. This will be sigma sub c for clock errors. We'll call this sigma sub e for ephemeris errors. There's another kind of error that we don't really get anymore. Selective availability, or SA. And this was about 32.0 meters. This was the intentional degradation that the US government would introduce into GPS just to make sure that the civilian GPS was not perfectly precise. And in 2000, they turned it off because they figured, well, you know, this is being used by so many people, and it's become such an important part of, you know, everyday life that we'll go ahead and turn it back off. But who knows? One day they could turn it back on. So it basically, they were, they would swallow like a chip in the PN sequence intentionally every so often, and that would introduce enough unpredictable error in the signal that you wouldn't be able to decode it without a special decoder. But normally, nowadays, this is actually 0. Ionospheric delay. Sigma sub I. This is one of the bigger sources of error. That's 6.4 meters. And that's a typical number. That's going to fluctuate throughout the day and depending on where you are on the Earth. Tropospheric delay. Sigma sub T. That's going to be about 2.0 meters. So troposphere is sort of the area of the atmosphere that has all the weather. It's the densest part of the atmosphere, the lower portion, and the ionosphere is above that. So even though this is denser and would slow down a radio wave more than the ionosphere, there tends to be less variability because you don't have this weird charge fluctuation. Receiver noise, and again, this is a typical value. In the absence of all other errors, this would contribute about 2.4 meters. Remember, Doc Cephas talked about this last time. We have to synchronize with the chip. And the resolution, the temporal resolution, is going to be proportional to the width of a chip, right? But if you think about it, you know, the waveform in GPS is chipping at about 1 megachips per second, which means a chip lasts about 1 microsecond. Now, how far does light travel in 1 microsecond? About 300 meters. Very good. Yeah, but so it's 1,000 feet roughly, pure, like the English system. 300 meters, 1,000 feet. That's a long way. So one of the things you have to do is not just look at, you know, sort of what bin that chip is arriving, but you have to look at the correlation peak, exactly where it occurs. And that's actually a very difficult measurement to make unless you have a very clean channel. So we'll see there's actually a signal-to-noise ratio dependency on this receiver noise figure. And then multipath, and again, this is highly location dependent. Multipath error, sigma sub m, on average this will be about 3.0 meters. Multipath is considered any reflection that you get off of the ground or a mountain or a tree or a building, and that will always arrive later than the first arriving component, which is what your GPS receiver will assume is the strongest component that comes into a receiver. And so this will degrade your estimate. And in some really rare instances, for example, if you're in downtown Atlanta and one of the big buildings blocks the satellite and another big building actually reflects another satellite and adds another 100 meters, 200, 300 meters to the path, you'll get some crazy estimates. And this will be a lot bigger. On the other hand, if you're in a cornfield in Iowa, you might even do better than 3 meters. So recognize that a lot of these are just average values. Now, as often happens in life, when you assume Gaussian statistics, and you also assume that these errors are independent. That's a nice assumption, right? You know, why is there any cross-dependence between my ephemeris error and thermal noise error that I get from my receiver? You wouldn't expect there to be. And in that case, what normally happens is this is a good formula for life, not just GPS errors. But your RMS error, whenever you have independent phenomenon contributing to errors, is always the square root of the sum of the squares. So we square the clock error, square the ephemeris error, square the selective availability, square the ionospheric error, square the tropospheric error, square the noise error, square the multipath error, take the square root. And if we tallied up all of these on the other board, we would get 9.5 meters. And that's without selective availability. With selective availability, you get about 33.4 meters. So you see that makes a huge difference in the accuracy of your estimates for location. Why? Because the biggest thing in a formula like this is what dominates, you know. This is basically, we're taking a bunch of random variables. We have an estimate. You think of your estimate as sort of the ground truth, you know, plus some sort of error. If you assume your errors are separable, then you sort of have error 1 and error 2 and error 3, etc. And if these are all Gaussian distributed, and of course we know that everything in the universe is a Gaussian, right, when it comes down to it. Or at least it better be for engineering approximation. When you add these independent Gaussians together, you're basically taking what you can treat this as one gigantic Gaussian whose variance is the sum of the variances of the individual Gaussians, which means the standard deviation is going to be square root of the sum of all the squares. That's where that formula comes from. Makes sense. And in a formula like this, the biggest term is always what dominates. Selective error availability is the biggest contributing error. It was 32 meters by itself. So when you square it and then add all this other smaller stuff to it, take the square root, you almost get 32 meters. When you take selective availability out, it's probably the ionospheric delay that gives you the biggest problem. And you see that's, if we knock that down, this would go down quite a bit. Do we have a question or comment? Yeah, Abhishek.
How are we considering these errors independent? Because the ephemeris error will affect the ionospheric delay and tropospheric delay.
Or not? It shouldn't. It shouldn't. Remember, the question is, how could these be considered to be independent errors? And there may be some minute dependencies, but if you think about it, the ephemeris error is basically, oh, my satellite is just a few meters ahead or behind its course. And so the ionosphere actually doesn't change that much over that kind of region. It's sort of like if it's raining here, you know, if I move a couple meters ahead or backwards, it's going to be raining over there too.
It depends on the angle, the elevation angle. You probably look at the vertical is less.
That's right. That's right. And that's not going to change much either. If that starts to change significantly, your satellite is no longer healthy. You know, something has drastically gone wrong, and you probably shouldn't be using it in a range estimate. So you're right, though. There are going to be some slight, nothing is ever completely independent, right, in a statistical nature. There's always some goofy cross dependencies that are very difficult to predict. But for the most part, these are pretty, almost as independent as you can get. William.
What does this differential GPS work to knock down so that your signal is like 40 centimeter accuracy?
That's a great question. So the question is, which of these can we knock down? And it turns out that some of these on the list, if we go back to this list over here, some of these we don't have any control over. Take a look at receiver noise. Can we do anything about receiver noise? No. It's unpredictable. There's one thing we can do about it. We'll talk about that in a second. But for the most part, I can't do anything about that. Multipath, can't really do anything about that. Ionospheric delay and tropospheric delay, if I know the local conditions to that, I would expect I could calculate most of this out. So this, let's put red check marks for you, those of you viewing at home. Be a multimedia color presentation. These I might be able to get rid of. Of course, this one, it got turned off, but if I had a selective availability receiver, I could have still read it. Ephemeris error, if I have a nice receiver, GPS receiver, that can decode that ephemeris error information on there, that gets tracked very carefully, I could probably get rid of most of that. And this I should be able to get rid of too, if I synchronize with the clock. So this is the stuff that differential GPS or augmented GPS is trying to get rid of, those kind of errors. In the absence of these other errors, that's when your receiver accuracy gets down to like 3 meters or less. And then to get down to the 40 centimeters, which is what Grant's talking about, that's when you need some supplemental technique. So you're using GPS and something else locally to do some correction factors. We'll talk about that in a bit too. It's okay. Any other questions so far? Oh yeah, Abhishek.
Can we use GEO satellites to improve the performance by correcting the ephemeris errors or
GU satellites.
GEO satellites?
GEO. Oh, they don't in practice. And my guess is that using geostationary Earth orbit satellites, I'm not sure if there's a way to, you're getting basically the same data that you'd be getting from the medium Earth orbit satellites that GPS has. So I'm not sure how that would help you. But in practice, they don't do that. Now, what you can do in the case of differential GPS is you use a fixed known location that has an active GPS receiver. And it does things like measure the ionospheric delays, because it knows precisely where it is. And it knows, basically can calculate what that ionospheric extra delay is. And then it can transmit that, it broadcasts that on a separate channel. And that would be an example of how to augment the system. Oh, yeah, you have a question or comment?
Like, what is the theoretical limit on the GPS error based on the chip rates? Like, we can go to
that's a great question. Let's talk about that right now. Good lead-in. So I just mentioned that if we are trying to resolve a chip, they put in pictures what we were talking about earlier. So, we have this chipping sequence, a random set of +1s and -1s, and we're trying to resolve with a temporal measurement precisely which chip and when it actually started. And this is the chip that's about 1 microsecond wide in the time domain, which means our ability to estimate based on just chip position, if we just kind of look at the changes, we're going to get about 1,000 feet of error if we do it that way. Say 500 feet error, plus or minus. But of course, if you correlate this, you remember from your last homework what the correlation spikes look like? You correlate this thing, and then there's a noticeable peak in time when you do the correlation. And if you try to key off of that peak, you need a clean signal, but you can do a lot better than just 1,000 feet. So intuitively, we know that the chip size is going to appear in a rigorous formula that translates signal parameters to position. And there's actually a very rigorous way to do this. I'll just present the result here. But whenever you talk about radio location, there's this thing called the Kramer-Rao bound. And the idea is this. Okay, we're measuring something in electrical engineering. It could be time difference of arrival, which is what we're looking at in GPS. Or it could be signal strength, or it could be angle from an array. But basically, we make a measurement, and that measurement has a quality to it. It's not a precise measurement. We didn't get the exact same thing. There's going to be some sort of signal to noise, or whatever your metric of degradation is. There's going to be some error associated with it. So you have a signal input plus a noise, and then you perform mathematical manipulations on that signal, and you get something like XY or XYZ out of there, plus a position error. If there was no noise or uncertainty in this measurement, there wouldn't be any noise and uncertainty on this measurement, right? So the Kramer-Rao bound is a way to rigorously map. If you know the math that's going on here, you can take the uncertainty in your signal and map it to the uncertainty in the output. And there's a standard technique for that. Any kind of position location system, if you're ever doing a master's thesis on it or PhD dissertation topic on it, one of the first things you always do is derive the Cramer-Rao bound. It's just a mathematical bound for mapping information and uncertainty through a mathematical algorithm. It's one of the first things you compute. And it sort of gives you the lower limit of what the precision can be for whether it's a GPS receiver or receive signal strength location algorithm. So I don't believe they derive it officially in your book, but I have a student thesis on my research website. His name is Jet Zhu. He was my first PhD student, and he did a location analysis for cellular using received signal strength. Maybe it might even do a special topic on that pretty soon. Just 'cause I think it might be helpful for what you're doing in your project. But he actually goes through and derives the Cramer-Rao bound for that kind of location system. So this is a standard cookbook procedure that you work through to do the derivation. But that looks it's a very different kind of location system than GPS, but the way that you set up and use a Cramer-Rao bound is the same. So anyway, let's reason what this should be. We already know that T sub C chip period should show up in the formula. Let's do a little thought experiment. If we were in one-dimensional space and we had a ground truth position where the x was and a 0 where the estimate was, my sigma sub R1D the error should drop as T sub C drops. So if I take T sub C and I multiply by C, the speed of light, or the speed of our radio wave, then this basically gives me that 100 or 1,000 feet of precision as my sort of my baseline for just being able to nail a chip. However, if I can measure this peak accurately, it should be a lot lower than that. If I have a nice clean signal, a little bit of noise might distort the peak. So we'd expect this thing to be some sort of inverse proportionality to the carrier to noise ratio that we receive at our GPS receiver. And that's actually the case. Square root of C over N D spread. So we take our raw C over N that's coming into our receiver, and then we add our processing gain, which is going to be 40 dB in a GPS receiver. And that's our baseline formula. So if we have a good D spread carrier to noise ratio, say 20 dB, we'll get 1,000 feet up here divided by square root of 100 down here. So then we'll get down to about 100 feet, 30 meters. And that's good, but we know that our GPS receiver is a little bit better than that. And so one of the things that you can do to get your signal to noise ratio down, you don't have to do just one bit. So the processing gain for one bit is about 40 dB because it's got a 30 dB processing gain for a single code, 1,000 chips in the code before it repeats itself. And one of those 0.02 second bits that get sent will actually have 10 of those repeated. So GPS is one of a few signals where the frame length, the repetition length of your spread spectrum code is actually smaller or different than a bit period. There are actually 10 frames of the same PN sequence, the same spread spectrum code within one bit frame. And so that's why you'll see different numbers kind of bandied about. The the ability to reject interference in a GPS system is based on the fact that you have 1,000 chips in the code, and you can reject about 30 dB of self-interference or system interference, co-channel interference. But in terms of noise, you'll be able to reject 40 dB for each bit that you're decoding. And there's no law that says you have to stop at a bit for your decorrelation, right? To decode the bit, you got to stop at a bit. But if you want a really accurate measure of when precisely that exact correlation happened, you can correlate over several bits. So look at try to line up your phases and do a correlation, 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 correlation. When you get to the 10th correlation, just keep on going. And the phase might flip because of the bit, a different bit might get sent. But that's no problem. Just keep correlating. And so there's another factor that you can put in here. Call it T int over T bit. So a cheap GPS receiver will integrate over 1 bit period, 20 milliseconds. Let's call this averaging interval. So cheap GPS receiver averaging interval will be 20 milliseconds. 20 over 20 is 1. This will be a factor of 1 in your calculation. Well, that's pretty lame. That won't do much. But if you do 20 bits or 100 bits, this is how a lot of GPS receivers crank up their accuracy. They'll just sit there and integrate on each bit, on each satellite spread spectrum stream coming in. And it's effectively like averaging. They'll calculate a correlation period, and then another one, and another one. And each one will have a little bit of noise added to it. But if you average a whole bunch of them together, this underlying triangular structure is still there. But the noise should average out, and you should get a really clean correlation peak. And that's basically temporal superresolution, if you've ever heard that term. It's averaging again and again and trying to pin down very precisely, far within a chip period, when the true time of arrival was for this signal. People try doing this in the cellular industry for E911 location. That was always a bad idea. I mean, there's some systems in some instances where it works, but for the most part, a cellular system, your signal fidelity is so crummy because you have all this uncoordinated in-band interference. The signal fidelity is so crummy that it's really hard to get a precise estimate from that signal, aside from the fact that it also tends to be very narrowband. 3G systems are broadband enough to do that, but especially the early systems like TDMA, I think that had like 40 kilohertz of bandwidth, or GSM, that was like 200 kilohertz of bandwidth. That's actually a lot smaller than, or a lot larger in terms of its bit length, the symbol that you're keying off of. That's a lot larger than this. Coupled to the fact that you don't usually get a very good carrier to noise ratio. If you have a cellular system where you have really high carrier to noise ratio, you are like the world's worst carrier because you're not reusing that expensive spectrum that you had to pay for. So. Okay. Oh, yes.
This I didn't get this part. When this autocorrelation is when it is maximum, is at the most you can go at the chip period, the resolution is when they're exactly lining on top of each other. Then you get the peak of the autocorrelation. Right?
That's right.
But how do you get more than that precision? I'm not really.
Well, okay. So if there is the next chip over, if you were to delay a chip, you get a correlation that was like that, right? And so if you just sort of bin this out and step, like you were doing a coarse acquisition of of a PN code, just trying to see, is there a signal there? You would not expect to be able to tell more than a chip apart. However, there's this device that you can put in, and I think this is done in software now in modern day GPS receivers, but early on there was a hardware device called a delay lock loop, which would basically line this thing up very precisely. And I don't have a schematic of it, but it basically looks a little bit ahead and a little bit behind. It has multiple correlators on it. So it has one that's a little bit ahead and a little bit behind. And so if it starts to see some correlation kind of pop up, partial correlation pop up over here, it'll speed up your main correlating sequence. If it starts to see a little correlation pop up over here, it'll slow it down. And so it's sort of a really nice, precise way to measure the exact peak beyond even a chip period. But you have to have a really clean signal to work, to have this work. It's just like super resolution techniques in arrays, if anybody's played around with those. It's just the temporal equivalent of that. You assume that you have one nice, clean, multipath-free signal in the time domain. You're trying to pinpoint it very precisely. In array theory, they have super resolution techniques where you've got an antenna array, and you want to calculate very precisely which direction something comes from. Well, technically, we know in this class that an antenna array gets this far, this big in space, which means a pattern is going to be this big in a pattern domain. So, if you get a signal in that pattern, then you'd expect this to be your angular error. However, there are these other techniques where you can look at the signal and say, okay, it's going to have a plane wave structure. Therefore, it should wash across my antenna array with certain phasings. And assuming that a priori structure and a very clean measurement, I will be able to pinpoint beyond the resolution of my spatial array that this signal is coming from precisely this direction on the horizon, 63.059 degrees. And it turns out that those are wonderful techniques until you get noise in multipath. And it's the same reason. As soon as you start degrading the signal, this assumption that you have a very precise correlation, clean correlation peak breaks down, and you're pretty much left with just, oh man, did it show up in this bin, or did it show up in this bin, or this bin? You can't pinpoint it much beyond that. And we see that in this formula, right? As the carrier to noise ratio gets really crummy, if you've got just as much carrier power as you do noise, then you're pretty much stuck with this bin level estimation of when precisely did this signal actually arrive. Does that make sense? Did that answer your question? Oh yeah, Francesco.
Yes. How can we be sure that our system will reach the criminal bound?
The question, this is a great question. How can you be sure that your system will reach the Cramér-Rao bound? And the answer is you can't. It's a mathematical lower limit, and you're always going to do worse than this. But you can never do better mathematically, unless you sneak more information into the system.
But the real system, so we do some measurements and then we...
Yeah, chances are your real system are going to have some other sources of errors. You picked the wrong electronics, or you got some signal degradation somewhere on your board, or you took a shortcut computationally and did a cruder method that's quicker to compute, but it's not as accurate. And chances are this is going to be your lower level. That's why they call it a lower bound. It's a mathematical bound, but you're probably not going to achieve this. It's like Shannon channel capacity. If you get close, you probably say, oh, the problem is done. I solved it. But okay, one more thing before we continue on. This is not the actual formula. I put this as sigma sub r 1d. That is, if you're making a single measurement and trying to solve a one-dimensional position using this technique, we're using 4 dimensions. 3 dimensions for x, y, z, and then we need the 4th satellite to actually synchronize the system and get the offset like we talked about last time. So, okay, now pay attention. This is the part that confuses the heck out of students. So let me try to explain this as cleanly as possible. in GPS, your 3D formula is going to be square root of the number of satellites that you use times t-chip times the speed of light divided by square root the carrier to noise on d spread square root of t int over your averaging interval over your bit period. Okay, and for 3D, we need 4 satellites. And this term really comes into play just because you've got 4 dirty measurements being folded into your estimation of range, and that range is going to be so many meters off. And so it's going to increase because you use more pieces of information that had, each of them had a certain uncertainty to it. So that's why this goes up. Now that's a little bit counterintuitive, and I have to qualify this formula here. You say, well, wait a second. What if we use 17 well, we don't have 17. Let's use 8 satellites that are visible. Do I plug in 8 here? And if so, I would expect it to get better if I had extra satellites. And the answer is yes, it does get better if you use extra satellites. And this is not the formula for that case. This is for the maximum number of satellites that you are required to use. So if you're doing a 3D estimate, you plug in 4. If you're doing a 2D estimate, you plug in 3. Because you need time and then XY. You're doing the 1D meaningless case that we were studying over there, you plug in 1. If you have an extra satellite, your GPS receiver has to come up with some sort of new algorithm for how to handle that extra information. In some cases, it'll just take the ones with the highest carrier to noise ratio and throw the rest of them out. Well, in that case, then you use either the average, you put n equals to 4 and you use sort of the average carrier to noise ratio, or if you have some more clever way of using that information in a mathematical algorithm, you have to sort of derive a new Cramer-Rao bound for that particular case. Does that make sense? 4 satellites, 4 dirty measurements, the range actually gets worse from our 1D case. That's not to say that more satellites are bad. It's just that beyond 4 for the 3D case, you need to do some extra math to come up with a new expression, or just some simulations in that case, to figure out what the Cramer-Rao lower bound is. Okay, any questions so far? Oh, yes?
What you were discussing with Rafi, like maximum resolution that we can have is, it depends on the sampling rate at which we are having our signal. It doesn't depend on any chip rate or anything. We are sampling like 4 samples per chip rate per chip. That means we have 4 samples, and the resolution is restricted to the sampling rate.
That's right.
Sampling.
No, not in super resolution techniques. If you have a clean signal, you can actually get beyond your sampling rate in terms of resolution. But you're assuming a priori a structure there, that you have this triangular. So to get back to your, let's say we're double sampling our chip rate, right? Or let's see, this is not the best way to deal with that. Think of it this way: if I have another correlator in my receiver, and I have a clock that's clocking it faster than, or has precision well beyond my sampling range, an internal clock to my receiver, then I can actually get a crude estimate of where within a chip this peak was occurs. Because, for example, I can just basically say, okay, I'm going to correlate with a phase lock loop or a delay lock loop, and I know at 1.0000 such and such seconds that this peak occurred. I could advance my clock a little bit, and if this drops somewhat, I know that I've overshot my peak. If I slow it down a little bit and this drops just a little bit, then I know that I've undershot it. And so there's a special receiver structure that you can use to make sure to maximize that point. And if you have a very accurate clock in your GPS receiver, you can pin this beyond the resolution of your sampling hardware. The only problem is that it assumes you have a very clean signal, because as soon as you introduce some noise into that algorithm, the thing starts dancing all over the place. So high signal to noise ratio, 30 dB or higher, beautiful algorithm to use. Low signal to noise ratio, less than 10 dB, you're almost back to your chip performance. Luckily, you always usually get at least 20 to 30 dB, over 20 dB on a D-spread GPS waveform. So that means you can get a factor of at least 10 there, maybe higher. Depends on how good your receiver is. Any other questions? Okay. Well, this formula, there's another assumption built into this. I haven't said anything about the geometry of the satellites. And this sort of is a really good formula if the satellites are sort of uniformly spread around. In fact, you can show that the ideal geometry to triangulate a user with 4 satellites, what do you think it would be? Where would the satellites have to be? If you were floating in space and were equidistant from 4 satellites and you were using them to triangulate them, where would those 4 satellites be? They would be on the vertices of a tetrahedron, and you would be in the center. That would be the way to get them most spread out in space. It turns out being spread out in space gives you a lot of accuracy. Now, of course, that would never happen on Earth, right? One of them, you would have to propagate radio waves through magma to get to it, at least one of them. So recognize this is an ideality. There's another factor that you will see quoted in GPS and just about any other kind of ranging system. That's sort of another factor to multiply onto this value if you have particularly degraded satellite positions. Now, what do I mean by particularly degraded? Let me draw an example of what I'm talking about on the board. This will be a 2-dimensional example. Okay, let's say that I am doing an absolute time of arrival scheme estimate, which means that I have sort of I have a receiver. I have 2 transmitter 1, transmitter 2, and I have a time of arrival, absolute time of arrival estimate for each of these. That means that for time of arrival 1, that's going to define our radius about that first transmitter of a circle. This one, time of arrival 2, is going to be another radius. And of course, there's some uncertainty in that measurement. So maybe that radius is a little bit bigger. Maybe it's a little bit smaller. Maybe this radius is a little bit smaller or a little bit bigger. And I've drawn these intersecting at roughly right angles. And if you kind of draw out that region, a diamond-shaped uncertainty, it looks kind of like a square. And that's sort of the best case scenario. If we were to consider another scenario where maybe my transmitter and my second transmitter were over there, and maybe the point of intersection was over here. Well, then here, I got radius 1 about this transmitter, radius 2 about this transmitter. And of course, each of those has some uncertainty about it. So maybe that radius is a little bit smaller. And I'll try to draw it with the exact same uncertainty level. And maybe this radius is a little bit smaller. And maybe this radius is a little bit bigger. So I've drawn roughly the same amount of uncertainty as I did over there. But you'll notice that if I kind of draw in that same diamond area, it's a lot bigger. What's more, it's kind of oblong shaped now. I would expect to be closer, more accurate in this horizontal direction than I would be in the vertical direction.
That diamond that you're drawing, does it have to be within some proximity of the receiver? Because in the first case, there's another region where they do intersect, and that's at the bottom.
That's correct. So ignore the ambiguity for the moment. You're right, there's an ambiguity there. But just for the point of illustration, I'm trying to illustrate the uncertainty. So yeah, you would need technically another receiver or some other piece of information to resolve the fact that, oh yeah, this could be the spot too, down here in the intersection. In fact, technically, there would be another intersection point, over there somewhere for this as well. And technically, in GPS, you have that problem too, because you think about it, the code repeats itself every 1 millisecond. So that means you could travel 300 kilometers, and the code starts repeating itself. So if you were 300 kilometers above the Earth's surface, you would actually not know what phase of the code that you were looking at. But since you live on the Earth's surface, usually you can get rid of those kind of ambiguity points by just throwing them out and saying, well, I'm either here or I'm 350 kilometers above Atlanta. And since only a handful of people have ever been into space, we can eliminate any point that occurs above that. But this phenomenon of geometry-dependent location performance, we have a terminology that we use in all location sciences called dilution of precision. That's what this phenomenon is. So you will see this abbreviated as DOP, dilution of precision. Some people will call it the geometrical dilution of precision, GDOP, if they're specifically talking about the geometry of where the radio transmitters are. And of course, if you want to be very precise, they use the term HDOP and VDOP. Horizontal dilution of precision, vertical dilution of precision, if you want to differentiate between how bad you're doing in one particular direction versus another. So imagine you're on the Earth's surface. Your satellites are mostly overhead. You don't have anything back here as much as you'd like to. That would be the ideal situation. So based on the formula that I put over there on the board, the GDOP, the typical GDOP that you would multiply by that for an average set of GPS satellites above you, well, the HDOP turns out to be pretty good because you got some spatial variety across here. So your horizontal dilution of precision is about 1.16. So you multiply that by the error estimate that we put over there on the board, and that gives you the true error estimate of GPS for a typical dilution of precision error if your satellites are not ideally spread apart. VDOP is a little bit higher. GPS doesn't do quite as well with vertical ranging. That's going to be 1.26. And your total 3D PDOP, position dilution of precision, is really the square root of your HDOP squared plus VDOP squared, and gives you a factor of 1.72. So that's the true 3D position dilution of precision, by the fact that we don't have ideal satellites. Keep in mind that this is an average number. During the course of the day, the GPS satellites are zipping around. There may be a pathological situation where either because of the time of the day and the location you're at, or just because multipath or a mountainside is shielding you, that you might actually get some really bad PDOP, just because all the satellites that you can read are over in this part of the sky. And that's very terrible for any type of radio location type system. In fact, when I was doing some work in the cellular environment, where we're looking at trying to find 911 calls, that people that dialed 911, we'd had to find them using some sort of information on the cellular network. The worst kind of situation, like when you're in Atlanta, it's actually not that bad because you've got cell towers all over the place. So if you have a cell phone here, and if you're measuring signal strength or even time of arrival, you just, chances are the cells that you heard somewhere over here, somewhere over here, somewhere over here. So you had good dilution of precision, a low value of PDOP. The worst kind of situation would be when you were out 85, maybe 10 miles from Atlanta. The only cellular stations that you could communicate there with were along the highway in what we call a string of pearl configuration, string of pearls. So if you think about that, they're all lined up in one direction. And so you might be able to get forward and backwards very accurately, but there'd be this huge region of uncertainty perpendicular to the highway. You weren't sure if the user was over here, or maybe they were a mile over here, or a mile over here in this cornfield. And so this is a true story. So one of the dilution of one of the time of arrival companies that was selling a time of arrival solution, they had a technology for fixing this problem. They would basically snap to the closest highway along this string of pearls. And they called this technology road sucker. That's the best, isn't it? This is the beauty of engineering. We always name things exactly after what they're doing. It's sucking the estimate to the nearest road to overcome this dilution of precision. Yeah?
Will time of day also affect the ionospheric delay?
Yes. Yes, it does. Time of day affects the ionosphere, which is why it's something that's somewhat unpredictable. Yeah, Josh?
All the GPS receivers use the dilution of precision information to pick the best satellites to use.
That's one of the criterion. So it's sort of an interesting kind of algorithm, and every maker of a GPS unit has their own algorithm. They'll look at dilution of precision to select the satellites. If they can hear more than 4 satellites, then they'll make sure that they fold in the ones with the best dilution of precision. Of course, you wouldn't want to use a satellite that marginally increases your GDOP, but has maybe a 5 dB worse carrier to noise ratio. Then you would be shooting yourself in the foot in terms of your ability to do super resolution. There's all these factors that you have to consider, and everybody's algorithm for actually calculating GPS in those conditions is sort of proprietary. They don't really publish the details very much, and you have a lot of freedom as a designer to do that. But there's sort of some complicated weighting scheme, I guess, with GDOP, carrier to noise ratio. I don't know, what else could you use? Anything else?
Isn't there also a time dilution of precision?
Time dilution of precision. In the way that GPS works, the GDOP is sort of a time dilution of precision. It's the temporal uncertainty and it's how the geometry maps the temporal uncertainty into a positional uncertainty. But you will see some systems use different terminology. You will see, especially in hybrid systems where you might be using time of arrival and signal strength and some array antennas, if you've got that kind of hybrid system, then they may actually take the different types of dilution of precision for each mode of your location and call it one time dilution of precision, and the other one angle dilution of precision, the other one receive signal strength dilution of precision, something like that.